Alrighty, worksheet 26. So it's things that you theoretically can figure out on your own, but I'm going to give you some hints. So there's no new material in this unit, okay? But there is something called a temperature model that is a pretty common thing that we give to calculus students, and then a couple other basic problems I want to show you. Okay, so temperature. So the way temperature works, when we model it, we usually talk about some object that's either colder or hotter than the environment. And if this here is the ambient temperature, it doesn't have to be at 0. If the item that you bring into the environment is hotter than the ambient temperature, then it's going to have this exponential decay towards the ambient temperature. But if it's colder than the ambient temperature, it does the same thing but in the other direction. Okay? So the ambient temperature is essentially taking the place of your 0. So your temperature of your object as a function of time is going to, let's just say A for ambient temperature, and then it's going to be either plus or minus depending on whether you came from above or below. It's going to be plus or minus like a PERT. This is a PERT question, but we put a minus in the formula to indicate that we're not doing the PERT formula in this direction. We're not going this way. We're reversing the flow of time, right? Because that's, if things are increasing, it's PERT, but it's decreasing. So we put a negative sign there to indicate that the R is positive, and we're going to affect that change in direction with a sign in the formula itself. Okay, so PERT, or in your homework, I think it's a K. Okay, so there's a K there. And so I actually tell you right off the bat, like, what is A and what is P, so you don't have to worry about that. But P is the difference between your initial temperature and your ambient temperature. Okay, so that's pre-filled in the worksheet, and that you need to figure out what K is based on the word problem. And the other thing you need to figure out is what you have to take the derivative of this function, okay? And you need to figure out what the initial slope is. I don't remember if it's cooling or heating, it doesn't matter. You've got to find out the original slope, and then sometime out, I ask you for the slope again, and what is the temperature of this object an hour out, okay? And you're going to round things to the nearest integer as necessary. So you're going to get a sense for about, how fast these things change. Change, like, for example, like my pen keeps deciding to stop working on me. That's for example. So if you've taken physics, you might know V equals IR and P equals IV. And so we're going to see these formulas play out in one of the exercises, but we're going to think of it this way. We're going to think of I, which is current, is V over R, and we're going to look at P is equal to V squared R. Now, why does that make sense? Well, actually, because if V equals IR, you can solve V over R is equal to I, and then we stick it in there, and then P is equal to V over R times V, which is V squared R. Okay, so that's all in case you're curious about that. You don't need to know that. What you really need to know is these are the two formulas that you're going to be working with. And so the other thing you need to know is that since your voltage is going to be constant in the problem, it's a constant, I think, whatever, 9 volts or whatever it is, these pieces here are not changing. So actually the only variable is R. The resistance is changing with respect to time somehow. So you need to figure out something about this problem. So the problem doesn't actually give you R as a function of, explicitly as a function of t, but it tells you that R is changing with respect to time. So what you want to do is think about what this means, and you need to read the word problem, because they tell you dr dt is given to you verbally. Okay, and then the other piece, I'm not going to show you what happens to P because it's exactly the same type of thing that happens to I. So it's going to be the same process. So here's the thing. You know what r is at the start of the problem because why? Because you have this I equals v over r, or v equals ir. You solve. You're going to solve for this missing piece. Solve to find your initial r value. And then what you're going to do is you're going to do the linearization on that. You're going to say, aha, r is a function of t is equal to r that we just solved for, the initial value, plus dr dt times like t. But t, you'll see this doesn't end up mattering that much, but this piece matters. This piece you have to keep track of, because if I take the derivative of r with respect to t, then this piece goes away for us, and all we really care is dr dt. So this is this should be times. I'm making it look like a function. It's times t. Okay? So the important part is when you go to take the derivative of r, all you're going to have is this verbal piece that you got out of the problem, and then you're going to plug it in where it's appropriate. Okay? So just be aware. You need to be aware of what the original resistance is, and dr dt you're going to get verbally, and so you're going to figure out how to merge all this together. So that's my clue for that one. So hopefully that clue is enough. Okay, and then the last question I believe I have for you is the classic boats moving. Sometimes it's things other than boats, but it's usually easier to put this problem with boats because you think about being out in the water. You can go north, south, east, and west. Now, let's be realistic. Boats don't actually travel like that. That's not usually how they decide to move, but it's just a theoretical model. There's something to put in your mind's eye. So you start two boats, usually somewhere on the axis, and you know where they are relative to each other. So maybe, I'm just going to make this up, maybe it's 4 knots on, one is 4 knots from the origin, one is 3 knots from the origin, and then these boats travel somehow. So maybe this boat is going north at 10 knots per hour. No, knot is 1 nautical mile per hour, so it already is in the right units. Okay, this boat travels west at, let's say, 5 knots, and then I'm just making up these numbers, and then you want to know how fast the distance between them is changing. You know, maybe they're talking to each other on a radio, and you want to know how fast that signal is going to deteriorate or something like that. So you're going to try to figure out what's the actual distance between them, and so you can say, well, at time t, this is going to be x is 0, y is going to be 4 plus 10 t, and then, for example, this is going to be -3 minus 5t comma 0. So obviously the numbers will be different in your exercise, but you want to express the location of the two boats in terms of an ordered pair, an x and y pair of coordinates, where you have t as the moving variable. So they're both, those points are both with respect to t. At this point, once you get that, then this whole diagram doesn't matter anymore. This diagram is completely irrelevant. We have to find the distance between these 2 points, and we already have the right triangle, so that's convenient. Sometimes these problems get more complex, but it's pretty. This is a pretty straightforward one. So the distance from between these 2 points. So because these two guys, the distance between them is just this -3 minus 5t, but you're gonna, square it. You're gonna square the other distance, so the distance between here and here. There's no subtraction necessary. Sometimes there is, but usually there's some kind of more complex structure, but this is a pretty straightforward problem. And so the distance is equal to the square root of this mess. Okay? So if you want to know how fast the distance is changing, then you can't work with distance squared. Like in some of our other exercises, we've dealt with distance squared, like if we want to minimize something. In this case, it's the actual distance we're asking about, and since we're not trying to set anything equal to 0, we're just talking about the change in the distance, then there's no shortcuts in that case. So you have to go ahead and take the derivative of this whole mess, and then you have to say like whatever the time is. So in your exercise, it gives you a time, it gives you in terms of the clock, and so you have to figure out what that means. And something else I suggest, so let's say you want to know how fast is this changing at t equals 10, for example. What I'm going to suggest to you as a sanity check is to calculate d at some nearby points and just do a numerical derivative, because by the time you're doing all this, it's rather complicated. So why not do the following, just to make sure you're not going insane. Do something like this: distance at 10.1, distance at 9.9, and divide by 0.2, and this should be approximately equal to d prime of 10. Now, I think I even asked you to do that on the quiz, something of that nature. I think I asked you to do that. So don't be surprised if I ask you to do that. But you should do that if you're trying to find the derivative somewhere and you have a really crazy function and you think you might have made a mistake. As a sanity check, do the numerical version too, just so that you know you're in the right ballpark. Okay? And that is all the hints I think you need for this worksheet. I will see you in class.